In this video, we're going to discuss some of the considerations for dienophiles in the Diels-Alder reaction. So these dienophiles are the 2-pi electron components, and these usually contain electron withdrawing group, and that actually makes the reaction occur faster. We're going to talk about exactly why that's the case a little bit later, but we can think about it in the way that because the dienophile is the electron poor component, if we do make that 2-pi electrons, those ones that are going to go and participate in the reaction, if we make that component more electron poor, we're going to have a better electrophile, and that's going to be what that electron withdrawing group is doing. It's going to be making that dienophile more electron poor or a better electrophile. So we have some common examples for withdrawing groups on the dienophile. So we have basically if you have a carbonyl next to the double bond, like in this example, in this one, a CN group, so a cyano group or a nitro group attached. These are some common electron withdrawing groups for Diels-Alder reactions. How these withdraw electrons, we can think about moving those electrons onto the oxygen, and then this resonance structure that would then bring those electrons kind of away from the two carbons that have that bond, and that's actually going to be withdrawing electron density through that resonance. You're going to have the same thing happening for the second molecule. The third one, the CN group, is a little bit tricky because this is the one where the actual molecule looks like this, so that carbon, we can still do that same kind of resonance for that one, except it's between a carbon and a nitrogen instead of carbon and oxygen. And then for our nitro group, that was another tricky one that we saw. So the way that that actually looks, that nitrogen is going to have those charges and also a double bond to an oxygen, so we can do that same resonance. We also have a permanently formally positively charged atom right next to the double bond, and so that's going to withdraw as well. So if we were thinking back to the aromatic section, we would classify these types of groups as either moderate or strong deactivating groups. We're going to see that those are usually going to be our electron withdrawing groups for our dienophiles, are going to align with what we saw as moderate or strong deactivating groups for aromatic rings. We also have to consider the stereochemistry of the product when we're using dienophiles if they have a group on each end. So with our 2-pi electrons here, we have a group on the bottom end and also on the top end, and how they're oriented in that original dienophile is going to make the difference in terms of what the product's going to look like. So in this reaction, we have our diene. We're not talking about the diene right now, so we're going to use the same diene. And then we have a dienophile on the right-hand side. This dienophile is, if we take a look at the H's attached here, this one has the groups on opposite sides of this double bond. And so what that's going to translate to when we do the reaction is that in the product, those groups are going to be on opposite sides of the ring as well. And we can classify this as an E substitution pattern. So we have the phenyl and the other high priority group on opposite sides of the double bond. So it's an E double bond. And just remember that we did, when we were trying to decide if it was E or Z or what, we were assigning priorities. So for double bonds, to decide if they're E or Z, we're doing our priorities based on atomic number. So H would be the lowest atomic number. So this one will be number 2, and then 1 would be on this side. And we do the same thing at the top, 2 because it's an H, and then 1 because it's a carbon attached there, so that has a higher atomic number than the H. So priority 1s are on opposite sides of the double bonds. And then if we draw our reaction out, we're going to see that those groups are going to be on opposite sides of that ring. So how we're going to do that once we make those carbons sp3 hybridized, throughout the course of the reaction is we're actually going to have to show wedges and dashes. So we show the wedge to show that that group's coming out of the page, and then going back into the page is the other group. We could have done this exactly opposite, so we could have made the aldehyde group going back into the page and this one coming out. As long as they're opposite, that's what matters, and that's because they were on opposite sides of this double bond. We have the Z double bond down here, so we have a Z dienophile where our groups are now on the same side of the double bond. And so what that's going to mean is that in our product, they're going to be on the same side of the ring. So let's go ahead and draw that, just that mechanism out. And this one, we're going to have those groups on the same side. So it doesn't matter if we made them both going back into the page or if they're both coming out of the page, as long as we're going to have them on the same side of that ring. And so we, with our E-dienophile, with those groups on opposite sides of the double bond, we end up getting that anti product, and we got the syn product when the two groups were on the same side of the double bond. So very important to pay attention to if your dienophile does have two groups attached to it, kind of one on each end. You do have to be careful in terms of how are they oriented with respect to one another. Opposite sides of the double bond are going to mean they're going to end up on opposite sides of the ring, and we do have to show that stereochemistry. For the Z dienophiles, if they're on the same side of the double bond, they're going to be on the same side of the ring, and we do have to show that stereochemistry as well. So it's something to kind of look out for our dienophiles.